So it's a real pleasure to get to introduce Nils Reimers. He's the director and principal scientist of machine learning at Cohere. Before that, he authored some really well-known research papers on SentenceBERT and the popular sentence transformers library, which those of you who have been working on this week's project in the Search of Machine Learning class are using this week. He worked as a research scientist at HuggingFace, co-founded several web companies, and has been a consultant in investment banking, media, and IoT, the Internet of Things. He did his PhD and postdoc at the Technical University of Darmstadt in Germany in natural language processing under the supervision of Iryna Gurevych at the UKP Lab. And today he's going to talk about the challenges and recent progress in large-scale multilingual and cross-lingual search, the main ingredients of a large-scale multilingual search system, and how recent advances and deep learning can be leveraged to build more effective and more efficient retrieval models, simplifications using dense vector representation, semantic search and cross-lingual search and language bias, and first and second stage neural retrieval models. This is a real pleasure. I hope all of you enjoyed it as much as I know that I will. Nils, over to you.
Great. Yeah, it's a pleasure to be here. Thanks for the kind introduction. Yeah, I'm a German, so I really care about multilingual search. It's also, if you're in Europe, the French border, the Italian border, the Czech border, the Polish border are really close. So for Europeans, it's like really natural to think more than beyond English and say, okay, we want to have solutions that not only work in English, but also works in many languages. But soon, if you build it with lexical search, that it's one of the most painful experiences you can have as a search engineer. And here I'm like a big advocate for like multilingual semantic search, and will explain why I think it's amazing and why I'm motivated about this. About me, I've been doing embeddings for quite a long time. So probably in search, a lot of people are hyped about semantic search, which was really different when I started, which was back in 2018. There was like no really that many embedding models available. No training code was available, which was super frustrating for me. So I started to learn, okay, how can you train these embedding models? Made the code available in the SentenceBERT or sentence transformers library, and educating a lot of people how to train the models. And then people found it more and more useful, and also the models got better and better. And now you have this rich ecosystem of model providers, vector databases, courses, and so on. We've been working a lot on also evaluation. Big bottleneck for a lot of models is like poor evaluation. So researchers, they try to hill climb like some bad evaluation benchmark, and then the model's not really getting better. So I've been focusing a lot in my research career on like, how can we benchmark and how can we really evaluate where do they work and where they don't work. And it's always interesting. If you improve your evaluation, you see how quickly the community reacts to it and finds better models that work a lot better. At HuggingFace, have been working a lot on like how to adapt models in a zero-shot setting. People ask me all the time, hey, how can I apply these semantic search models to my, I don't know, patent search or medical search or media search? I said, yeah, if you have training data, here's the code. And I say, sorry, I don't have training data. So worked a lot on how to adapt these models without training data. And then last year joined Cohere as director of machine learning. And at Cohere, what we're doing is we train foundational models as a service. The one is generate model. You give in a prompt like create a blog article, why co-rise, and the instructors of co-rise are amazing, and then it provides you the blog article. This is done by my colleague Phil. I'm responsible for text understanding with a strong focus on search, which is our primary focus, but also classification, content recommendation, and content analyzation, where we train large language models up to 100 billions of parameters and provide it as a service for you. And I really think so currently people are hyped about GPT-4. I think what's really interesting, the next one is when you combine text understanding with generate models. So if you think about if you prompt ChatGPT, GPT-4, or generate model, Claude, what do our employees think about our benefits? It will produce some output, but it will not be like, okay, what our employees think about our benefits. Also, if I prompted like what has been discussed with this client so far, it will produce maybe something, or it will reject and say, sorry, I can't answer this. but it will not give you like any useful things. And how you build it is like by 3 components. So you take what do our employees think about our benefits. You pipe it to a search engine that has, in the best case, all your enterprise data, like every data piece you have in your company. Finds the relevant information, which could be some employee survey, which you run in this quarter. Then you analyze the results. So you got like all the responses from this employee survey. And you generate, and then you say, okay, based on the employee survey from Q1, the most beloved benefits in our companies are based on responses employees want an improvement in. And similar, you can do it with content, with CRM data, for example, from Salesforce. What has been discussed with the client so far, you search in Salesforce or whatever you use for CRM, you analyze it, you generate, and then you get like output you have discussed so far. And in the next meeting, you promise to follow up on these points, and then you can see, oh, shit, I forgot to follow up on these points, so maybe I should do that. So today, more focusing on search. So this full search stack, how it looks like in a simplified way is the following. So you have some index server. Traditionally, this has been something based on Lucene or Elasticsearch. You have a first stage retrieval, also traditionally based on inverted file and like lexical search. So find all documents where this word is mentioned. And then you go, or more recently, people more focusing on semantic search using dense vectors and then using a vector database. And then the output you take here is what you typically pose to a second stage model, which is a more powerful model where you re-rank, for example, the top 1,000 hits you get from the first stage, where you also take like other ranking signals into account, like recency, popularity of the results, page rank, and so on. So whatever feature you find interesting. And then you present traditionally for a really long time, you put out like these top 10 results hit from Google. And then you have some feedback, which can be in e-commerce, people buying some things on Google, people click something, they bounce. And then you try to take this feedback to make your first stage and your second stage model better. More recently, what people found really interesting is to have this conversational interface where you have these chatbots on top of the results and be able to chat on this. So this is like a really recent component, which you now find in the search stack. And yeah, what we're focusing on in our search areas, like to provide the machine learning tools for these 2 stages, first stage, second stage, and also conversational interface and feedback loops so that you get state-of-the-art models in these areas and really take in like the latest research results from machine learning and information retrieval. I'm a big criticizer of keyword search. I'm not a fan of keyword search because it sadly performs really poorly. And we're sadly find it in so many places. So I'm a big advocate to really switch it up and make it better. And if you look at Wikipedia and you have a really simple search query, what's the capital of the United States? The first entry is capital punishment in the United States. And Wikipedia, it's one of the most popular websites in the world. The search engine is like a highly tuned, I think something on Lucene Elasticsearch, highly tuned lexical search. So it's not even like the naive implementation, but still the search results are really shitty. So if I know Washington, D.C., yes, I'm able to find Washington, D.C., but if I don't know what's the capital of the United States, there's no way how to find it on Wikipedia. And that's probably why no one is using the search bar on Wikipedia and everyone bounces to Google and types it into Google to find the page on Wikipedia, which is like really frustrating. For web data, it's okay. Everyone goes to Google or Bing and poses the search query there, and then you go to the respective website. But if you have like internal data, like your emails, your Notion, your Slack, your Google Docs, or your Word documents on a drive, it's really frustrating that even simple search queries not really working that. And it becomes even more painful if you care about multiple languages. In English, what you typically do is you tokenize on white spaces. So you find any space or tab or new line between tokens, and then you say, okay, these are the tokens. Then you do some stemming, and then you do some stop words in English, and then you put it in your index. But if you go to Chinese or Japanese, there's no white spaces in Japanese. And for Japanese, the big question is like, how do you tokenize when there are like no white spaces? There are like 3 different strategies. you can apply to tokenize in Japanese. So you need to figure out, okay, which one is the best one? And probably, so I don't know much about Japanese, so I'm not really able to judge as a search engineer what's the best approach. And totally what you do in the end, what you end up is like a system like this. So you run some language identification, you check what's the document, what's the query. You need to check, okay, find what's the language in it. And then when it's English, you send it to a special English pipeline tokenization stem or stop words in a special English index. When it's Spanish pipeline, you need to design in a Spanish index. If it's Chinese pipeline, you can't use white spaces. You need to use different stemmings, different stop words. Goes to some special Chinese index. And then quickly what you identify is, yeah, lexical search sadly doesn't work that well. So if you search for color with the American spelling, but someone has document with color with the British OU spelling, it will not find this. So what you do is like you add a component to the English pipeline to detect synonyms, variations, spelling variations. But this is like not really generalizing. So it's if you do it for English, it doesn't work for Spanish or Chinese. So companies do a lot of engineering to create these individual pipelines, maintain it. And if you have to do it like for 100, 200, 300 languages, it becomes really painful. And what's a bit frustrating for me as non-English speaker, as a German native speaker, I know a lot of companies, they're sadly just tuning the English pipeline, really putting all the magic in the English pipeline, like synonyms, spelling corrections, spelling variations, and say, yeah, the other languages, they're nice, but it's like too small. So they say 50% of the customers English, 50% of the customers are non-English, but sadly the non-English users are too fragmented. And then if you search in German, your search experience is even worse than what you get in English. And I don't know, probably for other languages is similar. So I think there's really a time to change this paradigm. And with semantic search, you will see it will be a lot easier and also a lot better. So big focus from us has been how to do semantic search across languages. On the one side, it gives you much better results. On the other side, it gives you also much better, it also works across languages. So I can show you some small demo here. So for example, if I ask a question, how's the weather in Toronto? Here I have Wikipedia available in different languages indexed. If I run it out of the box, lexical search with Elasticsearch, it over-indexed on the word weather. So it thinks weather is the most relevant term. So top hit is like studying how the weather works on other planets has been helpful for understanding how weather works on Earth. And sadly, none of the paragraphs I retrieve is like really relevant and gives me information about how is the weather in Toronto. In contrast with semantic search, which I will show in a minute, you find the first entry is from the Spanish Wikipedia. And okay, Toronto winters sometimes feature short cold spells with maximum temperature below -10 degrees Celsius. And it gives me a really relevant results in many different languages. Second is like about from the English Wikipedia that Toronto has like 4 distinct seasons. And it's also able to change the alphabet. So for example, in the top 10 results, I find something from the Korean Wikipedia. If I translate it, I get the information Toronto has a cold, humid climate and exhibits typical Southern Canadian weather. So it's like really, on the one side, the search results are much nicer. It works across languages, which creates super interesting use cases for many settings. And also, as you will see, it's like a lot easier to set up and maintain. So what is semantic search? As far as I know, this will be like covered in depth like next week in the lecture. So just to give like a brief glimpse, what is semantic search? So the idea of semantic search is you work in vector spaces. So every document you have from Wikipedia or somewhere else, you project it using some machine learning model to a vector space. And then when a query comes in, like how is the weather in Toronto, you also project it in the same vector space. And the models were trained so that the relevant documents are close to the query. So when I ask like, how is the weather in Toronto, that the article talking about the weather in Toronto is close in the vector space. And then in the vector space, you can do like this nearest neighbor match. How does it work on a more deeper level, technical level? What you have is some transformer architecture, for example, based on a BERT architecture. You put in the document creates like contextualized word embeddings for all the tokens in the document. You apply some pooling operation to get like a fixed size vector at the output. And you do the same with the query. You put it into the transformer network, you do the pooling, you get the vector, and then you can measure like the similarity between these two vectors and say, okay, how close are they on a semantic level? And then you can use it with some vector database and be able to search in this area. What's nice is that this vector representation it's not grounded in the language you're using. So it doesn't care if your text is in English, like two dogs in the snow, or if it's German, zwei Hunde im Schnee, or if it's Spanish, or if it's Chinese. You can train the model so that independent of the language they're using, it's mapped to the same vector space. And this makes it really easy to search across languages. So if I search like where are the two dogs, I would find like all these information. So I can even put it into like search in Arabic, like where are the two dogs? And I find these information that the two dogs are in the snow. What's also really nice, it's from an engineering perspective, it's a lot easier to set up. So you don't have these 100 different indices, these 100 different pipelines, which you try to extend. And then you have 100 different Elasticsearch indices, which you need to scale and chart and backup. But everything is the same system. So you have one model that's a multilingual transformer model where you can put in your document and your query in 100 languages. It projects it to a vector space. The vector database doesn't care, is it English or German or French? It's just like a vector. So it's just like points in a vector space. And then you're able to search on it. So within 5 minutes, you get an extremely good that works across 100 languages. It's super easy to deploy, super easy to manage. And what's nice, if you improve like this pipeline and get like a better embedding model, it's beneficial for any language. So if you have like more training data, like you teach the model how to deal with misspellings and so on, it's beneficial for any language you have. So it's no longer you only focus on the English one, but you get like improvement for all the languages. And with a lot of customers we're working, they have been so far working with lexical search on English. And then when they switch to semantic search, they don't see some improvement with semantic search for English, but they see like really large gains for other languages, and also especially for a lot of Indian languages, because they say, okay, all these Indian languages, it's not really a focus for us because the market is too small. But now we have this unified model and system, and you see really large gains for all other languages. And as mentioned, setup, sorry, that's the wrong window. Setup is really simple. It's like a few lines of code where you say, okay, these are the text, you pass it to the embedding model, and then you insert into your vector database, and it doesn't care like what's the language. So it's like really easy to set up and extend, and you no longer have to think about, okay, how do I deal with like mixed languages? How do I identify the right language of a document? How do I scale like the individual indices and so on? So to go a bit more on a technical level, so how do you train these embedding models? One popular method, or the most dominant, widely used method, is the negative ranking loss, or also constructive training. There are like many different ways how to call it. And there, the idea is you have positive pairs, which can be, for example, a query and an answer passage, or it can be a question and a duplicate question, or a paper title and a paper product, or in e-commerce, like a query and the product you purchased. And what you want is that the positive pair should be close in the vector space. So A1 and P1, they should be close in the vector space. So if you search for A1, let's say a query, and P1 is a product, you want to find this product, while all other products should be distant in the vector space. And this is like what you constantly optimize. You take these pair, you say, okay, this pair should be close and all other combinations should be distant. And then you train the model on this. To give an intuitive explanation, for example, you have like question answer setup. You say, how many people live in Berlin? And then you say, okay, the positive is like around 3.5 million people live in Berlin. And then you have other passages in the collection, like Washington, D.C. is the capital of the US, and the 21 Olympics are held in Japan. And you compute the similarity between the query, and the passages. And you say, you get, for example, these as an output. You say, okay, this is my prediction about the similarity. I know how I set up the task that A1 and P1 should be close. So here I want to have a really high similarity of 1. And for A1 and P2, P3, I want a low similarity of 0. And then you train the model. So it's quite easy. It's also quite easy to get the training data. And then you get like a nice vector space, which you can use for the semantic search applications. So this is the basic how to train it. There's a lot of knowledge how to improve it, the training. One simple thing is a larger batch size. So what we see here is like the number, how big is the batch size. And then we see like the performance, how it's increasing with larger batches. You can see it as like a multiple choice test in an exam. For example, you have a question and then there are like 10 different answer possibilities. That's like easy by random guessing. You have a 1 out of 10 chance to get it right. So if you did not learn as a student for the exam, but if the professor increased it from like 10 answer candidates to 1,000 answer candidates, it's a lot harder to guess it right. And so the more answer candidates you add, the harder it gets. But sadly, on the same time, it makes it more difficult for training because you need like more GPU memory, the larger the batch size. So you have to really balance it and say, okay, what's doable with your hardware and how can you maybe at some point try and distribute it if you want to scale to really large batch sizes. The other option, which is nice, is to add hard negatives. So here you train with triplets. So you say, okay, A is the anchor, P is the positive, and then you take in some negative. And you say the N should be similar to the positive, but it should not match with A. So for example, good example would be how many people live in London. And then you say the answer is like around 9 million people live in London. And the negative would be around 1 million people live in Birmingham, second to London, where you say, yeah, this text is really similar to the positive, but it's not providing the answer to the original question. There are also bad negatives. For example, bad negative would be London has a population of 9 million people. So yes, the negative is similar to the positive, but sadly it's not a negative because it's also a valid answer. And so a lot of ML engineering goes into how do you define these triplets? How do you make them really hard so that it's really close to the positive, but still not a valid answer to the question. And that's at scale is quite challenging. But there are like certain ways how you can automate it, like in e-commerce. A could be like a product, like a search query. P is a product you search for. And N is another product you have visited or which you clicked or which has been shown to you, but where you decided to not buy them. So now we can go to multilingual and cross-lingual embedding models. There are different ways how people tried to do multilingual, cross-lingual embedding models. Big challenge, sadly, has been so far that for English, there's a lot of training data available. So we have like great data sets like MS Marco from Microsoft, where you have 500,000 search queries in English and relevant documents. But this is like sadly really lacking for most languages. So people tried to find like other ways how to train these multilingual, cross-lingual embedding models. One old approach is the laser approach from Facebook. It was before transformers, using LSTM networks from machine translation. So in machine translation, we have a lot of these pairs. Okay, this is the English sentence. That's how it should be translated to Chinese. And what Laser did is take this machine translation system, like an encoder-decoder system, and then take the output from the encoder as a text embedding. So here the issue is that we cannot really learn what's represented in the vector space. So what should be close, what should be distant in the vector space. So it works quite poorly if you want to use it for search. It only works well if you want to use it like for translation. Similar in 2020, Google proposed the language agnostic BERT sentence embedding model. I'm also using data from machine translation, but now using it in a vector space where they say, okay, we have these two indices, a source text, a target text, put it in a vector space. The translation should be close in the vector space, while non-matching translation should also be distant in the vector space. So here the positive, query positive pair was the translated pair, but sadly it performs poorly in identifying like similar sentences or also for search. Quite nice approach, which is also a bit older, is from Multilingual Universal Sentence Encoder from 2019, also from Google, where they say, okay, we have these tasks that educate the model how to perform in search. So for example, from conversational responses, you say that's the input, that's the response. So we have take these tasks from English, and then we also add a bridging task, a translation task, where we say, okay, the embeddings of two texts in different languages should also be close in the vector space, which works much nicer, but has like challenges in getting the bridging task right, requires very large batch sizes. And it's also a bit hard to extend it to like new languages. In 2020, I proposed a method known as multilingual knowledge distillation. So there I was really frustrated that you only get these great models in English, but not in other languages. So what I did is taken a good teacher model, which you trained in English. And then from machine translation, you take parallel data, which you get like plentiful for all types of languages. And you initialize a student model. And then you take the original English sentence, pass it to the teacher model to get like the teacher English sentence vector. And then you pass the pair of the English vector, the English text and the English translated text to the student model, where you get a vector for the English input and for the German input in this case. And then you minimize the distances in the vector space. And this is like a really nice way how you can take any teacher model and make it multilingual. Like, for example, when the CLIP model from OpenAI was published, that allows to do like semantic search on images. Sadly, it was only available in English. So I took like the CLIP model in English, throw a bunch of translated text from machine translation to it, and really got quickly within half a day a model that works extremely well in semantic search for images in 100 languages that can be used for zero-shot classification of images in 100 languages. So it's a really nice approach. Final approach is the multilingual constructive training approach, which we had previously. So the previous approaches, they are based on alignment. Say, okay, this is the goal space. So English, that's the lingua franca we're using. And then you try to transfer many languages to like the English space. But this has the issue that the model has a really strong English bias. So if you do this, for example, then the model knows in 100 languages about all the US tax forms and how to file taxes in the US and what do you need to get like retirement in the US. Because the English models, they know a lot of things about the US, but they have never seen questions, answers, topics that's relevant for other languages in other countries, like in Germany. How do you do your taxes? In Korea, how do you file for retirement? So better approach would be like constructive training, where you get like these question answer pairs in 100 languages to really capture the interest and the topics of different languages in different countries so that the model works in Korean also for people and topics that's relevant in Korea. Challenge, however, is like, where do you get these large set of question answer pairs? So what we did last year is to crawl a large set of question answer pairs from the web. So that's always like a good source. So in English, people already provided like an MS Marco. For other languages, you have to go to Common Crawl it from there. First challenge was how to remove irrelevant pairs. So for example, what we saw in many of these pairs is you have the question, and then you have these cookie consent banners, or please sign up, or please pay here to read the article or read the answer. So we had to remove these. If it's just English, it's easy to do. But if it's like in 100 languages, so how can you identify sign-up pages in like 100 languages and remove it? Then extend it to triplets, go to like question answer, go to question answer negative, clean the triplets. On the one side, false positive, where you say, okay, that's a question, but that's not really answering the question. Or false negatives, that's a question, that's the answer, but that's sadly not a negative, but also good alternative answer to the question. And then once we have the clean data, we ended up with like roughly 900 million English triplets and 450 million non-English triplets. And then training these outside of training on a large compute cluster and getting a nice embedding model out. Interesting topic in this direction is language bias, which is a bit less well known. So language bias is the preference of certain language combinations by the embedding model. So for example, if you put in like an English query, do you prefer retrieving English documents, or should it, if there's a better document in Chinese, should it prefer the Chinese document on your query? And depending on the model, you can see that there is sometimes really strong language bias. So for example, in this LABSE approach, which uses machine translation, we see that English and Russian vector space is like nicely separated. And also for laser, it's a bit separated, but then for other models, not separated at all. And it's a philosophical question. Do you want to have language bias or not? So there's no clear answer to it. So side effects with language bias is that same language results are ranked higher just because of the language. And there might be better hits or answers in other languages, which can be like a pity if you miss them. But there are also arguments for language bias. So you got the user preference. So if I search in German, I probably prefer reading like a German answer compared to a Chinese answer. And also there's like a higher confidence by the model. So if I pose my query in German, it's easier for the model to check, is it really providing the answer for me, than when the answer is like in Chinese. So it's the same with humans. So if you get a result in a different language, you're a bit uncertain or less certain if it's really giving you the right answer to the query or not. There are also interesting effects if you have models without language bias. So for example, you do like search on images, which you can also use with the same vector approach. You embed wedding to the vector space, and then you embed images to a vector space. And then you see, okay, if I search for wedding, I get like an image like this. Where you say, okay, that's perfectly relevant. If you now have a model, such a vector embedding model without language bias, the model does not know anything about the language. So it's not captured the information, what's the language. And the challenge is if someone searches in Hindi for wedding, this Hindi word for wedding will be mapped to the same point as the English word for wedding. Hence, we will retrieve the same image, which can be a bit weird. So probably someone searching in Hindi might have a different perception how a wedding looks like. So probably person searching in Hindi is from India. So probably they are more interested in images, how a wedding is celebrated in India than in the Western or American world. Similar, when I ask who is the president, yeah, we can assume, okay, yeah, who's the president, bias, US bias, Joe Biden is the current president. If I search in French, qui est le président, should I assume that this person is interested in Joe Biden? Again, if I don't have a language bias, I don't have the information, what's the language, so I take what's most dominant in my training data, which is probably the US president. So here I would also say, yeah, Joe Biden is the current president, but probably if someone searches in French, they are more interested in the French president and want to find like information on the French president. So it's an interesting philosophical discussion. Do you want to have language bias or not? What are the impacts? For many use cases, you want to have some language bias to really capture these language country-specific properties. But for other use cases, you say, okay, no, I only want to find the best result and not, it should not be inflicted or impacted by the language. First and second stage retrieval. So first stage retrieval is what I presented, what you do with like these vector spaces, and then with a vector database, or you do it with lexical search, and then with lexical search, for example, on Lucene. And it's like really cheap. You go from 100 million documents to 100 documents. So it's like really narrowed down from like a massively large search space to like a small set of documents. And then what you typically do in the deployed search scenarios is to have a second stage where you take a more expensive model, which can then take in other ranking signals. So you take in these 100 documents from the first stage, you take in other ranking signals, use like a larger, more complex model. And here you get like a much higher quality at the end. And also what's nice about second stage retrieval, that it's easier to update an A/B test. So if Google deploys like a new first stage embedding model, so they train a new embedding model, they have to embed the whole internet again. They have to put like the embeddings for the whole internet into a second vector database and then do an A/B test and see, okay, will this first stage model be better than the existing model? And in most cases, as with A/B test, the answer is no. So then you will discard it. So it's like really hard and expensive to do like an A/B test on the first stage retrieval. But on the second stage, it's like super easy because you're just re-ranking these 100 documents. So there's no state saved. So it's really easy to update, to train it daily, to deploy it on like a small fraction of your traffic and see, okay, is the second stage model be better than the first stage? And if this is the case, you increase the traffic you send through and then you deploy it. So a lot of focus is really on the second stage retrieval, and you try to keep the first stage retrieval like in a really cheap way and ensure that the recall in the top 100 documents or whatever you used is good enough. Interesting approach we're currently working on is to educate the generate model how to search. So right now, generative models, that you give in the prompt and then it generates a text. What we're teaching is that the model is able to search. So similar what we saw 2 days ago with Bart or with like Bing Chat, like how can they search and also know what to search. So when do I need to search in my emails? When do I need to search on Slack? When do I need to search on LinkedIn? When do I need to search my documents? Or when do I need to search on Google? So this is what we're currently training these generative models to take the command, see, okay, where and what do you need to search for? Can be external APIs, internal databases, taking the output of these responses, put it through a re-ranking stage, and then take the command, the generate model, and say, okay, this is like the further information I got. Now you can create like the output. So if I have a question, what have I discussed with my clients so far? Goes, for example, to the Salesforce API, gets the information, what I discussed with the client so far, paste it into the command model, the generate model, and gives me like a nice generated output. Okay, to conclude, so lexical search and semantic search, there are benefits to both. So it's always quite good as a search engineer to know what are pros and cons of both. It's not that semantic search is always much better than lexical search. On my website, you can find many talks where I talk about all the shortcomings of semantic search and where it performs really poorly. And to give a brief highlight here, lexical search is really cheap. That's nice. It can search on long documents, doesn't have any length limit. Works really well when you have like multi-fields like title, body, and text. Keyword search for unknown. It's obviously good for keyword search. It's also good when you search for unknown words. But challenges with lexical search is like low search quality out of the box in many cases, that you often need like feature engineering to make it better, to be robust to spelling mistakes, spelling variations. And sadly, it's also like language dependent. Semantic search, on contrast, you can get like higher search quality. Synonyms and related terms are often covered by the model already, can be language independent, and you can search across languages, but it's more expensive to operate. Long documents and multi-field search still is a headache how to implement it. So there are some hacks how to do it, but it's still hacky. Doesn't work that well for keyword search. So if you say I have a specific error code, I want to find all documents containing this error code, that's very easy with keyword search, but it's hard with semantic search. And also it's harder to interpret. So it shows you some results with keyword search. I know, yeah, it contains the words I'm searching for, but for semantic search, it can be some arbitrary random noise where user asks, okay, why do you show me this search results? It has absolutely nothing to do with what I was searching for. That's so much from my side. Looking forward to the questions you have.
Yeah, thanks so much, Nils. That's awesome and dear to my heart. I started off in the search space working in cross-lingual and can attest to all of the hard problems that you brought up here. We got a lot of great questions from the audience. I'm not even quite sure where is best to dive in, so maybe we'll just go in chronological order, or at least as I see it, chronological order. Shrug asked up at the beginning, how does document level embedding work? Are there any models which can generate embeddings for large text documents like Wikipedia articles?
There are no such models, and there can also not be such models. So even if you right now we're on the edge to be able to scale these transformer models to like longer and longer context, but it sadly doesn't work with semantic search. So semantic search, these vectors, they sadly can only encode like a single fact. So it works really nice, semantic search, when the text is really clean and encodes like one information, and it struggles as soon as you put like multiple informations in it. So for example, in e-commerce, when you say I have a jeans and this jeans is available in the color blue, red, and yellow, if you do this with semantic search, it extremely struggles because it has these conflicting informations that the jeans is available in many colors, and it cannot put it into a single vector. And vector approaches for longer documents, the longer the document is, the more information and different topics you have in the document, and the more blurry becomes the vector. So even when it's fundamentally technically possible from the model, the search quality will be quite bad. What you do instead is you chunk your document, so typically on a paragraph level or on a fixed window level, and say, okay, every paragraph I embedded, put the paragraphs into the vector database, and then I'm able to search on a paragraph level. But there you have, again, challenges. So what I say here, semantic search for long documents and multi-field, that certain things are out of context, and then the search quality is not that good.
That's great. I'll keep going. There are lots of questions, but again, we'll try to do them in the order. Somebody asked, in the case of multiple negative ranking loss, does it matter if the length of the question and the answer are quite different, and that the expert examples talk about symmetric and asymmetric search? Maybe more broadly, you already alluded to the challenges of long documents, but how do you handle sensitivity to length with the variance in the length of on the search or question side, but also variance on the content or document side?
Yeah. So to me, it's not a challenge. So you can take like a query, which is 5 tokens long, and take the answer, which is maybe 500 tokens long. So it works quite well. So that's not the big problem. As mentioned, at some point, if the answer is like too long, contains like too many different facts, and the model does not know on which fact should I focus on. So if you have like topic ABC in the answer, the model does not know, should I focus on A and put it like where I store the information on A in the vector space, or B or C. And sadly, what the model often does is put it somewhere in between of ABC, which is like a really horrible place in the vector space.
Yeah, and maybe following up, I think there's some questions that kind of fit into this general theme of dealing with the data that's coming in, how clean it is. And so somebody asked, are there any scripts to identify good or bad triplets that we can customize for our own data? We have annotations from users. I think you broadly also talked just about how do I make sure I'm putting in the right types of things to make sure I'm getting the outputs that I want.
Yeah. The models are extremely sensitive when the negatives are also valid answers to the query. So if you have a triplet like how many people live in London, the model gets on this really bizarre thing where it tries to put like A and P close, like this two should be close, but A and N should be distant. And so it really tries to figure out, okay, why should this be close and this be distant? Is it maybe due to the lengths that I put like inputs with the same length close in the vector space and inputs with different lengths like distant in the vector space? So it really gets extremely confused. Hence, data quality is extremely important. On the one side, there's like ways how you can try to get it. So I don't know, you from click logs or so on, or you have like user votes like in online communities. You can also do like stage training where you first train like a first model on some set of the data, and then you do a scoring. So you take the initial model, you do a scoring, how close is A and P, how close is A and N, and say, okay, if the distance between these two is like too little, you discard the example. And then sometimes you also do a kind of lot of cleaning on like length, where you like check, okay, is the answers, is it long enough and not too short, and so on. So a lot of tricks really goes into like data cleaning, where I always recommend to really look at the data, see, okay, the triplets you have. And then from a perspective, doesn't make sense that A and P is close and A and N is really distant. And then if you see, okay, in many cases, you notice this doesn't make sense, then you need to go back and say, okay, how do I get my data and how can I improve the process there?
So it's another question, which is, I'm sure when you see a lot, even though it's specifically in the context of multilingual embeddings, people ask, would these embeddings work in their particular technical and business domains because these are large foundational models, or do you have to fine tune, or how do you fine tune? So I guess broadly, how do you see these kinds of transfer learning questions?
Yeah, so semantic search sadly has the challenge of like domain adaptation or domain transfer. So it works well on the domain you train it, but it's like really brittle if you transfer it to like another domain. There are like different ways how you can balance this. So one approach, which is nice, is like using these more powerful second stage cross-encoder models that are less sensitive to a domain shift. Second approach is to combine lexical search and embedding search. So here, this is sometimes called hybrid search. You run like lexical search, I don't know, Elasticsearch, BM25 in conjunction with semantic search. And then you combine these two scores, where people also show, okay, it works really good in a domain shift setting. Or there's like approaches to generate artificial training data. So there's some method I published, GPL, generative pseudo-labeling, where you take a generative model to create training data like triplets for your domain on a large scale. And then you train the model on these triplets for your domain. So you ask like the generative model, hey, here's a passage, create a good query and like a hard negative for the query. And then you train the model on this, and then you get like an in-domain model. So these are like all approaches that work quite well.
Another audience question, so many good audience questions here. Just how does the quality of the embeddings factor into all of these things?
Yeah, so that's another good point. So as we scale up like the training data set, the more and more domains it has seen, and the less critical is this domain adaptation, because when it has been trained on 2 billion triplets, it has already seen a lot of domains, a lot of variations. So here we see less benefit from domain adaptation, but it's also hard to find for us good evaluation data sets. Because when you have trained on everything, and then you also train on like data sets that are really similar. So maybe you have an evaluation data set in programming, and then okay, there you see the current model really drops in terms of quality, and then you have a million questions in computer science to it. And then you no longer see the drop on computer science because you already trained on 1 million or 10 million of these questions. So it's for us hard to really find these specialized domains anymore. And the goal typically is to really get in all the domains into the model, or as many domains as possible. But still in companies, you have like these company internal language product projects and so on, which a general foundation model is not aware of. And that's like a big research question. So how can I learn these company internal, and also from like little data? So often you don't have like millions of documents talking about your project, but maybe one document talking about your project name. So how can a model learn this?
Cool. So here's a very pragmatic question, right? In the two-stage approach described, essentially, it was doing like a semantic retrieval. There was a first and second stages, but somebody asked, how do we combine semantic similarity with other signals? And the illusion in the second stage is where you're using signals aside from relevance, popularity, recency. Is it something as naive as just getting a cosine out of the sort of semantic retrieval and then having that as a feature? How do you mix the query dependent and query independent?
Yeah.
Thanks.
So second stage, there are different type of models available. Classically is like these learning to rank models, which has been strongly built on XGBoost, like gradient boosted decision trees, where you would take from the first stage, like the cosine similarity, plug it together with other matrices like popularity, recency, user voting, like star rating of the product. And then you do like learning to rank on a gradient boosted decision trees. But people also explore more complex models on transformers, where you model cross-encoders, where you model query and document together. Because then the model is able to do like a word-to-word comparison. So it's already on a text level much better. And then you can add other ranking signals additionally into the training of the transformer network. So slowly you see more and more of these transformer networks are deployed as a second stage retrieval. They're expensive. And here in search, we're also always fighting with budget. So we need to see, okay, what's like the best search solution for a given budget? So here we need to see, okay, what's like a good trade-off in these settings to really say, okay, optimal solution. But without budget, you can deploy like multi-billion parameter model in the second stage. It will be super expensive, super slow, but amazing results.
Yes.
Continuing on, so many good questions, and Nils, and we probably could go on for a long time here. I don't know if you have a hard stop or not, but we won't keep you too long. If you had to build a language pipeline, this question actually has a lot of sub questions to it, so I'm just going to ask the more general one. You're going to go out and build all this stuff. How do you think about where to start? What are the key components that you need to put in place? Obviously, feel free to plug here as well. How do you think about getting started with these kinds of things?
Yes, so first question is probably, do you want to train your own models? Do you want to use one of the model providers, which has both pros and cons? Depending on your use case, maybe you want to train your own models if you have the expertise and want to build up the expertise and like host and run these. But for many other cases where you say, okay, it makes sense to build on top of the model providers, you can just plug in like the retrieval model from Cohere and plug in the re-rank model from Cohere and get like nice results out of the box. Then question is also for where do you store your documents? So this is always like a interesting hot topic. Do you stick with Elasticsearch? Do you use Vespro or Pinecone or Qdrant or Milvus? So there's like a long debate between the older, more established solutions and the challengers in the space. And then this really depends like which features do you need? Do you want to have like certain features people often use in Elasticsearch, like aggregation, which are not really available in these more newer vector databases, or do you purely want to stick on vector databases? Also filtering. So in e-commerce, what we often see is like these thousands of filters you have in the left menu bar on price, memory size of the laptop, screen size, budget, and so on, color, when can it be shipped. So here you really need to see, okay, what will be the requirements and what are the right tools to use. And then big challenge we find for a lot of users is like these, how do you break it down to make it suitable? So if you have longer documents and you have like multiple fields, which you have in most settings, how do you make it work with semantic search? There are like different ways how you can segment it. Maybe you need to add certain context. So on Wikipedia, for example, you break it down into paragraph. In each paragraph, you pre-print it with the document title. This works for Wikipedia, but for others, it doesn't work. And then also, how do you identify paragraphs is a challenge. How do you ensure that it's only like a single topic per text chunk? So there are like many questions people have in the field where you need to do experiments, build up stuff, and see what works.
So I want to get one last question from Emma that goes pretty deep, and also to give you a chance to just honestly pitch whatever you'd like about Cohere to us. It's been an amazing talk. So Emma asks, with regard to long documents, transformer self-attention encodes positional data effectively, and we see that in generative models. Is it possible that with higher dimensional embeddings or some other structure, we could embed things like multiple colors mentioned in the same sentence, but not mixed, right? Really get the structure in there. Are you seeing that happening?
Yeah, I think it's a fundamental problem of these dense vectors. So if you think about like colors, let's say in like a two-dimensional space, I can put like all the colors in a two-dimensional space. but I'm not able to put like combination of 2 or more colors in it. There are ways which we're researching and working on. One which I'm really interested in is like multi-vector approaches. So not take your document and map it to a single vector where you try to encode that the genes is available in blue, red, and yellow, but encode it as multiple vector where you say, okay, this is a genes. The genes is also available in blue. The genes is also available in yellow. The genes is also available in red. And then be able to search for this. So if you search for genes, it matches with genes. If you search for navy genes, it matches with blue genes. This has a challenge because you get an explosion of vectors. So before you had like one item becomes like one vector. Now one item can become 100 or 1,000 vectors. And this makes semantic search really expensive because all the vectors are in memory. And then you maybe propose it for an e-commerce setting and say, yeah, if you spend like $1 million a month for the vector database, you get this amazing search solution. But I say, sorry, our budget is more like $1,000 a month to get like a search solution. So at the end, it's again, finding the right trade-off. And this is constantly changing what's the right trade-off.
That's great. So I wanted to give you a chance. I don't know, a lot of the folks on this call, I think, work in industry, in search, how they can get in contact with you or Cohere, they can learn more, anything, any parting thoughts you'd like to share with us?
Yeah, sure. So always happy. So if you want to find good solutions, if you have any of these use cases and say you want to harvest the power, but you don't want to build like a billion training triplets and clean them and train your own system, feel free to approach us. If you want to get started, we have really good out-of-the-box models, have soon really good tools to adapt it to your specific use case, and can really help you to build these solutions, be it for search, classification, recommendation, or any generate task, and soon also a combination of generate, text understanding, and generate.
Thank you so much. I know I'd reached out to you, I think, a couple of years ago. It's a pleasure to finally get to hear you speak and really appreciate the depth of this presentation that you brought. So on behalf of all the co-writers, thank you so much.
Great. Thanks. Thanks, everyone. Have a nice day.
You too.